Okay, so we are all set now. So, any questions? We were discussing about the general principles of member design, and we discussed about the flexural capacities. I mean, it's the similar ideas as you would normally design compute the moment of ultimate moment of resistance of a section of given uh, concrete properties and the reinforcements, tension reinforcement, compression reinforcement. How do you go about finding the neutral axis as a function, as a fraction of the effective depth? Of course, the critical, there are only three things to consider. One is, of course, the compatibility, strain compatibility at different levels. Extreme fiber concrete and the yield tension reinforcement, centroid of tension reinforcement and centroid of compression reinforcement. What are the strains and how the strains are related to each other in terms of depth of the section and what is the neutral axis depth. And then of course there has to be equilibrium of forces, so net tension force is has to be balanced by the total compression force. And once you do this iteratively, you figure out what is the correct neutral axis depth, which will give us this equilibrium of forces. Then we find out what is the moment of resistance of the section, that is the capacity, section capacity, flexural capacity, depending on whichever is the prevailing condition, whether the concrete ultimate strain reaches first or whether the yield strain in the steel reaches is achieved first. And in order to control the crushing failure of concrete, generally we do not allow, we take care not to allow neutral axis depth to be more than 50% of the effective depth. So if that is done, then of course the crushing failure of concrete is avoided, and it will all we always look at the tensile reinforcement details. Similar things happen in the case of columns and shear walls as well. The only complicating additional factor being the axial load that comes into picture, and it is the combined behavior that we need to look at. But similar equations, similar relations, similar factors govern. Now, the next thing that I have been emphasizing again and again, it cannot be emphasized enough at any time, is the shear capacity or the shear strength of the section. Now, how does a reinforced concrete section resist shear? We have been saying that shear failure has to be avoided, has to be prevented, because that is a brittle failure. It is not acceptable shear failure is not acceptable. We just do not allow, do whatever it takes to avoid shear failure. So how do we do this? How do we avoid shear failure? Any ideas about the design to withstand shear? Of course, you must have done the basic. How the shear capacities are built in a section.
Then by providing stirrups.
By providing stirrups, that's right. So, how does a concrete section fail in shear? What is the mechanism? How does stirrup help? I mean, if you look at it, stirrups are vertical. I mean, the section is under shear, so it is clockwise or anti-clockwise. So how is this vertical stirrup going to help? Yes.
Here basically prevents from principal tension, which is called because the maximum shear is at 45 degrees to the principal plane, and the shear stirrup, some amount of force it is resisted by shear stirrup due to that. So,
yes. Yes, let us look at a typical section. So, there is a shear force here. Now, this shear will tend to distort this section. I mean, this kind of thing is going to distort this section into this shape. So effectively there is a tension along one diagonal and there is a compression on along other diagonal. Right now, obviously the concrete section is inherently strong in compression, but its tensile strength is extremely low. So you need to take care of this diagonal tension because of this shear, and that is where, I mean, if you have sufficient reinforcing, I mean, stirrups, lateral ties intersecting this line of tension, then they will be able to take up the this diagonal tension, and this kind of diagonal shear cracks, diagonal tension cracks which will happen otherwise will not be there, and that is very, very important in controlling the cracks. Right, this shear reinforcement, I mean, these shear stirrups, I mean, if they are not closely spaced, then you will find these cracks, tension cracks appearing all over the cross section, and sooner or later the section is going to fail in shear. And so this is what it is, and typically there are two ways of providing, I mean, this is what we call as the truss analogy. There are 45-degree tension and compression. So the truss members, we can look at this as a truss members taking these loads. So entire compression is taken by the concrete. I mean, you can look at it as a diagonal truss which takes care of this compression, and you need another another member to take care of this diagonal uh, tension in the by virtue of steel. And therefore, if you recall the detailing of reinforced concrete sections, sometimes although this practice is discouraged these days, but earlier times it was a very common practice because it used to lead to saving of steel, significant saving of steel. The practice of having bent up bars, your longitudinal steel, you would actually instead of curtailing it and then beyond a point and then of course extending it up to the development length, instead of curtailing it you would bend it up and then take it to the compression zone. So you would have different levels of reinforcement being bent up at different levels, right? And if you look at it, these diagonal, these bent up action, they are actually aligned with the diagonal tension of the that is required to withstand the shear. And of course, by taking this on the upper face, they also take care of these reinforcement, also take care of the tension at the top end when they actually terminate at the support. So there is going to be primary moment at the top end at the supports, and then main moment to be resisted at the bottom fiber in the center of the support. So this kind of reinforcement detail was very popular, and because it seemed to address two things simultaneously, adding more reinforcement where it is required, primary reinforcement, and also providing the adequate shear resistance directly withstanding the, I mean obviously if you look at it, if you are looking at the stirrups, they are only intersecting this tension at an angle. So this is full steel section is not being completely used. It is only a fraction component is that is being used, and it is more of a dowel action. But here the steel member is aligned along the required force, tension force that that is generated because of the shear, and this was thought to be a better, I mean more efficient use of the material. But the effort involved was much more. I mean obviously you needed much more skilled bar bending schedule, and the workmanship was required to be of a very high caliber to bend these bars correctly at correct length and properly mark them and then continue them beyond the bent up region. There is another issue here. This is fine as long as we are looking at only the gravity load design or monotonic load where the shear does not change sign, right? There is no reversal of loads. So if I am designing a frame, let's say okay. So if I am designing a frame for this kind of I mean static load, gravity load, obviously the direction of forces etc., the action that is taking place, the direction is known, and that direction is not going to change as long as the forces are not being withdrawn, right? So dead load plus imposed load, I mean, if you remove the live load, even then the change live load contribution is not really that significant, which will affect the direction of the force, direction of the action. But in case of earthquake load, if I am looking at, so but for earthquake load, this shear force, whatever you are looking at here, at one instant you have shear in this direction leading to diagonal tension like this. In another instant on the same section you might be looking at shear forces in this direction, so leading to diagonal tension along the other diagonal. Right? So in this situation, this kind of bent up bar schedule is not really helpful, right? And therefore this bent up bar is not really advisable, not really helpful in developing the shear resistance, shear capacities in the section for earthquake resistance, and we need to go for only the vertical stirrups. Only vertical stirrups or ties can provide reliable shear resistance. In beams. So and of course the capacities, what is the shear resistance, how do we specify? I mean, obviously the capacity depends on spacing of ties, increases close spacing of ties. Increases shear strength of the section. Right, and therefore at the location where you expect the plastic hinges to develop, in case of very severe earthquake, in the zones where the moment you allow the inelastic deformations to happen, the plastic rotations to take place in the zone. So these kind of locations where plastic hinges are allowed to develop, and of course there will be plastic hinge at the bottom of the so in this region of plastic hinges, particular care has to be taken to build enough capacities to withstand the shear and make sure that the section does not fail in shear, otherwise there will be a catastrophic failure of the section. And for this purpose it is important that the spacing of the ties has to be very close, and that is where the spatial ductile detailing provisions are there, which ensure that the while developing the flexural capacities, the ductility, enhanced ductility, I mean the confinement of course enhances ductility, but it also prevents the premature failure in shear. And by they will avoid by having more number of stirrups, closely spaced stirrups in the section. There will not be any possibility of any diagonal tension, diagonal shear cracks taking place, because those would be intercepted. The diagonal tension would be intercepted by the lateral ties, and obviously the lateral ties have to be designed properly. They have to be in sufficiently dense spacing and of sufficient dimension, sufficient cross section area. We should not, I mean the stirrups should not yield. Care should be taken to avoid yielding of stirrups or ties. Right? So if the stirrups yield, I mean what happens if the stirrups yield? What is wrong with stirrups yielding? I mean we are talking about ductility, enhanced ductility as a desired property. So what is wrong if the stirrup yields? Is it not ductile? Is it not contributing to the ductility? Any answers?
That it will weak the confinement of the concrete, so it will reduce the ductility as a whole.
It will lead to failure of the section itself, because I mean if the steel yields, obviously it is going to deform, and the strain will be transferred to the concrete. I mean because of the bond, there is a perfect bond between the stirrups and the surrounding concrete, and then if the steel yields, then obviously the strains will be transferred to the surrounding concrete, and the concrete itself will begin to crumble, and again the tension cracks will develop in the concrete. I mean the stirrup yields only when there is larger amount of tension then that can be taken care of by the steel. Then obviously the tension will be shared by the diagonal tension because of the shear will be shared by the concrete. and obviously the concrete will also begin to fail. So that is actually premature failing. It's again failing in failure in shear, which is to be avoided. And therefore, this has to be carefully designed. The stirrups and ties, design of ties has to be paid very close attention. And obviously, the code mandates that stirrups should not be of any less than 6 dia, but typically less than 8 dia stirrups are generally not used, because 6 dia is usually very uh, uh, it does not have enough buckling strength. I mean, most of the time, I mean, it is vulnerable to buckling, and it does not give adequate confinement either. So 8 dia is the minimum diameter that is to be used for reinforcing stirrups, stirrups or ties, lateral ties, and obviously there is a problem with using higher diameter, because it needs that much more effort to uh, bend it. I mean, the ties have to be bent into different shapes. I mean, rectangular or hoop or circular shape. So if you take too large diameter, then obviously it is not going to be that much more convenient. So has to be a play off between the two conflicting requirements. So generally 8 dia is the stirrups or lateral ties that are used, and that provides a good trade-off between the two requirements. And additional, if we require additional more shear strength in the capacity, more shear capacity in a section, then instead of increasing the area, it is much more worthwhile. It is a better alternative to reduce the spacing of the ties, provide the ties at a closer spacing, and that will have more stirrups crossing the diagonal tension line, and providing the adequate shear resistance. Of course, we will look at the mechanism, how this is done, but you know that the nominal shear strength at a site, at a section, comes from shear capacity of the concrete and shear capacity coming from the steel, right? So in case of plastic hinge region, the concrete capacities are assumed to be zero, and entire shear strength then comes from the reinforcing steel, and that of course depends on what is the pitch of the ties and what is the area of steel that is being provided at what interval, and so on. So that governs the basic requirement for shear strength, and that is essential for prevention of premature failure in shear, is essential for achieving high ductility. So prevention premature failure in shear is essential for achieving high ductility in flexion. So Now, what do we mean by ductility? We have been talking about this term quite a lot. Ductility is a useful trait, but what is the what do we mean by ductility? How many different types of ductility are you aware of? Can you elaborate ductility? What do you mean by ductility?
So plastic deformation before failure in a material is called as ductility.
Uh, please define again.
So plastic deformation in a material
Mm-hmm.
before complete rupture or failure is called as ductility.
Okay. So the capacity of the material to deform beyond the elastic limit is what you are saying as the ductile behavior or the ductility. So how do we measure it? I mean, now that we are talking about designing a section, so obviously we need to have some numbers. Design doesn't happen by just telling stories. I mean, so far we have been doing only that. We have only been talking of general principles, what should be done, what are the requirements of a good design. But so far we have not yet started dealing with numbers. I mean, at the end of the day, when you talk of a design, you talk of hard numbers. I mean, what is the cross section, what is the section details, and how those have to be calculated, right? So, in order to do that, you need to go beyond the conceptual definition. You need to quantify these terms. So, typically, in material testing, we define ductility, the common notion. If you look at in material strength of material or mechanics books, ductility is defined in terms of strain, ratio of strains. What is the ultimate strain at failure divided by the strain at the yield level? That is what happens when you do the tension testing of steel specimen, mild steel or high yield reinforcing bar. So you pull it and trace the stress strain curve, and whatever is the strain at the rupture divided by whatever is the strain at the yield level. So epsilon ultimate divided by epsilon yield is what you talk as the ductility. Ratio of ultimate strain to yield strain. So mu is defined as epsilon ultimate divided by epsilon yield, right? So so this is like epsilon y, this is epsilon ultimate. So this ratio epsilon ultimate divided by the yield strain is what is referred to as the ductility of the material. Now, obviously, this is defined for material testing itself. I mean, when you can pull the specimen in UTM and then carry out this kind of test. This is not really, this definition is not really very convenient for something that we deal with for reinforced concrete sections. So this is not, I would say, not convenient definition for characterizing reinforced concrete sections or so what is done? So if this is not suitable, then what is done for how the reinforced concrete sections should be dealt with? Any thoughts on that? What can we do? Or what do we do in case of reinforced concrete structures? And you need to go back to the first principles. How are the reinforced concrete sections designed? That's the basic deformation criteria you have. The strain distribution in a concrete reinforced concrete section. How does it vary?
Linearly, sir.
It varies linearly, isn't it? So let me just draw so this is the reinforced concrete section, and obviously the strain which is ultimate, I mean this is the concrete strain and this is epsilon s, epsilon c, and this is epsilon s prime. So compression stress strain in steel, in compression steel, right? So this is how the sections are deforming, and our purpose is to identify, or we are looking at the ductility of these sections. When we say plastic hinge, it is the plastic hinge that is developing over this section, and it has to flow. I mean, if steel yields, tension steel yields, then this is what is going to happen. The neutral axis will shift upwards for the same ultimate strain of the concrete. So what is happening what is happening if the strain in steel goes from this level to this level? It is this angle which is changing, angle of the strain block, isn't it? This triangle, strain triangle, is the basis of all our reinforced concrete section calculations. The neutral axis is derived from this strain block, strain distribution, because of similarity of the triangles, right? Tension triangle, tension zone triangle is similar to compression zone triangle, and everything, all the ratios, the basic ratio x by d, the neutral axis by to the effective depth, is derived from this, and it is this angle which we term as curvature. Right, and it is defined as epsilon divided by whatever depth, or d minus x. Right, so this is the neutral axis depth, effective depth, and this is the depth of the neutral axis. So this angle is equal to, approximately it's this strain divided by whatever is the lever arm here. So that is a measure of this angle, and so typically curvature is defined as the section rotation per unit length. So when we talk of the ductility of the section, we talk of curvature ductility. What is the ductility at the when we have this maximum deformation in the section, plastic hinge, completely plastic hinge case, full plastic hinge development. So what is the curvature at the maximum plastic strain in the steel, divided by what is the curvature at the on the verge of elastic limit of the section, right? So elastic limit we can work either from concrete or from steel, depends, and so then the curvature ductility is defined as ultimate curvature at the collapse and curvature at the yield point, right? So again, it is ductility is with respect to whatever is the ultimate deformation parameter divided by the corresponding value at the yield level. So if we are looking at the strain, it is ultimate strain divided by yield strain. If we are looking at the curvature of the reinforced concrete section, which is section rotation per unit length, so then we are looking at what is the curvature of the section at the ultimate level, at the ultimate state, collapse state, and what is divided by the curvature at the yield level. And at a structural level, we have another ductility, that is called the displacement ductility. Right, and this we can also say mu delta ultimate. Again, similar concept. What is the uh, displacement or drift at the failure, and divided by what is the displacement or drift at the yield level. Now, one thing that you need to understand is, I had hinted on this, about this in passing earlier, that ductility as a concept is defined. You are looking at a member level, individual member level, but when we use it in the structural context, it is not the member level ductility that is available, it is or even useful. We have to look at, or we have to ensure that the entire structure, which is an assembly of individual elements, that structure as a whole should be able to achieve or give us ductile behavior. And that in that context, this displacement ductility is often used. I mean, this displacement is often referred to as some kind of a macro deformation, such as the maximum roof displacement, ultimate at the point of under the lateral load, just at the verge of collapse of the system. And then what is the denominator is the what when the first yielding happens, so that is the yield level displacement. So this is typically done for you will find the pushover analysis or lateral load analysis. So that provides you this kind of global measure at a structural level. Now the ductility, available ductility at a structural level, at a global level, is often very small compared to the ductility that is available in the material, in the particular element or particular section that is undergoing plastic deformation. So it is very common, if you look at individual member or individual section, the ductility is to be of the order of 10 or 15. In this case, just as in this yield plateau, can be very large. It can be, this ductility can be of the order of 15 to 20 or even 25 for high yield reinforcing bars. But when we look at the structural level, even for this, even with this such high degree of ductility at the section level or member level, overall structural ductility is very small. So overall structural ductility global or structural ductility is of the order of 3 to 5. It's rare to have structural level ductility more than 5. It's very, very difficult to achieve. And that is why you will find that the response reduction factor that we have is of that order. Although you may worry, I mean, if you may wonder if you are looking at a ductility of the order of 15, 10 to 15, if we look at the member behavior, then why is the response reduction factor so low? compared with the ductility levels of 15, the response reduction factor, which typically accounts for inelastic deformation, energy dissipation by virtue of inelastic deformation, and that is only taken of the order of 3 to 5. So that is to make a distinction between when we look at the structural performance, we are looking at the complete structural performance as an integrated entity. We are not looking at deformations only at one section or in one element. It is the total deformation of the system which is of interest, and in that context the ductility level is much smaller than individual section level ductility. And in this context I will also mention, I'll also go back to the previous discussion on the shear. So what happens if the shear failure, if the stirrups yield in shear, then you will find whatever what is typically seen in improperly designed reinforced concrete elements. Their hysteresis is, they have a pinching, right? So it is not a very stable hysteresis. So they are pinched at the near origin. You will find that hysteresis tends to come closer to the origin. Instead of, if you see the hysteresis of well designed specimen, the hysteresis would continue to absorb energy, but in case the stirrups yield, then they lose this crucial energy dissipation capacity, and you will get pinching effect in the hysteresis curves, and obviously the energy dissipation capacity of the section is severely compromised in that case. And that's one more quantitative reason for or performance reason for not allowing lateral ties to yield. So you need to use the ties of sufficiently higher diameter and also at a closer spacing, whichever allows you to work with, allows you to work the bending as well as avoid the yielding of the stirrups or lateral ties during the alternating direction of shears during earthquake loading. Right, so I will stop here at the and